Welcome back. In this video, we're going to look at example problems involving Redington and full immunization. Let's get to it. All right, so here's our first example. A company has a liability of $53,000 due in 2 years. The company wants to immunize this liability at an effective annual interest rate of 5% by using a 1-year zero coupon bond and a 3-year zero coupon bond. Determine how much of each type of bond should be bought given that both bonds have a par value of $1,000. All right, so in this problem, the company wants to achieve immunization. They want to immunize their liability at an effective annual interest rate of 5%. So they want to achieve immunization at I equals 0.05. That is the decimal form of that 5%. Now, in order to achieve this immunization, they need to purchase a certain amount of these 1-year zero coupon bonds and 3-year zero coupon bonds. Our goal is to determine how many of each of those bonds the company needs in order to achieve immunization at this interest rate. And those bonds are going to serve as the assets for the company. All right, we know that they have a liability of $53,000 due in 2 years, and they're looking to immunize that by bringing in some assets in the form of these zero coupon bonds. All right, so to get started with this problem, the first thing that we should do is draw out a timeline and place in the assets and liabilities at the different times that they would be coming in or going out. And in this case, we're only going to need to include up to 3 years in our timeline because the liability is due in 2 years and we have a 1-year zero coupon bond and a 3-year zero coupon bond. So the most we need to look into the future is 3 years. So we'll start by drawing time equals 0. And then I'll draw the rest of the timeline here. Here's time equals 1, time equals 2, and time equals 3, and I'll label them. So here's t equals 0, t equals 1, t equals 2, and t equals 3. I'm going to place the assets at time t above the timeline and the liabilities at time t below the timeline. All right, now we only have one liability in this problem. The company has a liability of $53,000 due in 2 years, so that would be at t equals 2. So I'll write that in. We have $53,000 right there. And then for the assets, these are going to be those zero coupon bonds, which by the way, a zero coupon bond is just a bond that doesn't pay coupons, hence the name zero coupon bond. All it is a bond that pays a redemption amount at the end of its maturity. So for a 1-year zero coupon bond with a par value of $1,000, that just means that after 1 year, you're going to receive a redemption amount of that $1,000, assuming that the bonds are redeemable at par, which we are going to assume in this case. All right, so for the 1-year zero coupon bond, we're going to have $1,000 come in at time equals 1. And then in the same way, the 3-year zero coupon bond, which also has a par value of $1,000, and we're going to assume that it's redeemable at par, that bond will result in a payment of $1,000 at the end of year 3. So we'll have another $1,000 payment right there for that bond. All right, now those are our assets, but we don't know how many of each of those bonds the company needs, right? That's what we're trying to find in this problem. We want to determine how many 1-year zero coupon bonds and 3-year zero coupon bonds that the company needs to immunize their liability at an interest rate of 0.05. So, because we don't know how many of these bonds we need to introduce a variable that we can solve for. So depending on how many 1-year zero coupon bonds the company buys, they would have a payment of $1,000 at time 1, but that $1,000 would be multiplied by however many bonds they buy. So I'm going to represent that with x. We'll have 1,000 times x, where x will be the number of 1-year zero coupon bonds. So remember that the x represents the amount of 1-year zero coupon bonds, and then we'll use a different variable for the 3-year zero coupon bonds. I'm going to use y, so that means 1,000 times y will represent the amount paid at time equals 3, depending on how many 3-year zero coupon bonds the company purchases. All right, so once again, x represents how many 1-year coupon bonds the company needs to buy, and y represents how many 3-year zero coupon bonds the company needs to buy. And of course, that is in order to achieve immunization at an interest rate of 5%. Okay, now at this point, it would be appropriate to ask ourselves, is this company looking to immunize with Redington immunization or a full immunization strategy? Because the problem doesn't really tell us, right? It says the company wants to immunize this liability. It doesn't say Redington or full immunization, just that they want to immunize. And so it's up to us to determine which of those immunization strategies make sense for this situation. And the way that I would go about this is to first check to see if full immunization is even possible. Because one of the conditions of full immunization is the fact that every liability needs to be preceded and followed by an asset. And if you look at our timeline here, we only have one liability, and it is preceded by an asset, and it's followed by an asset, right? We have a 1-year bond at time equals 1, and a 3-year bond at time equals 3, and the liability is at time equals 2. It is sandwiched between two assets. And so it is possible that this company could achieve full immunization, which is a stronger immunization strategy when compared to Redington immunization. So that's going to be our goal here. Since we can see that full immunization is possible, we will work with the conditions for full immunization rather than Redington, which basically all that means is that we can ignore the third condition of Redington immunization. And if you're not familiar with what I'm talking about, feel free to check out my lesson video for this topic where I explain all of that in more detail. Okay, but as a review, here are the 3 conditions for Redington immunization in order to have Redington immunization at I equals I naught, or in our case, I equals 0.05. We have these 3 conditions. 1 is that the present value of the assets equals the present value of the liabilities. 2 is that the duration of the assets equals the duration of the liabilities, and that could be the Macaulay duration or the modified duration. It's up to us to choose which one we want to use. And then the third condition, which we're going to ignore in this case, is that the convexity of the assets is greater than the convexity of the liabilities. And that could be the Macaulay convexity or the modified convexity. Now, I said that we're going to ignore this because full immunization is going to be possible for our problem. And so we're just going to focus on these first 2 conditions, which are also required by full immunization. If these 2 requirements are met along with the fact that our liability is between 2 assets, then full immunization will be achieved. Okay, so from these 2 conditions, we will be able to set up 2 equations for our problem. We will be able to set the present value of the assets equal to the present value of the liabilities, and then set the duration of the assets equal to the duration of the liabilities. And that should allow us to solve for X and Y, the amount of each zero coupon bond that the company needs to buy in order to achieve immunization. All right, so if we go back to our problem, we need to set the present value of the assets equal to the present value of the liability, and then we'll do the same thing for the duration of the assets and liabilities. But let's start with the present value. From condition 1, we will set the present value of the assets equal to the present value of the liability. Now, the present value of the assets will be this $1,000 times X brought back 1 year to time equals 0, which is where the present value is valued. So we will multiply this amount for this asset by the present value factor to the first power. So we'll have 1,000 times X times V, and that will be added to the present value of this asset, which is 1,000 times Y, but this needs to be brought back 1, 2, 3 years to be valued at time equals 0, where the present value is valued. So we will have 1,000 Y times V cubed. Okay, and then this is going to be equal to the present value of the liability, which is an amount of 53,000 at time equals 2. So the present value will be that 53,000 brought back 2 years. So we'll multiply it by a present value factor squared. So we'll have 53,000 times V squared. Okay, so that's one equation that we can set up to help us solve for X and Y, but we still need to set up a second equation to help us do that. And that's going to use the second condition for immunization, which is that the duration of the assets needs to be equal to the duration of the liabilities. Now, I'm going to choose to use the Macaulay duration in this case. You could use the modified duration if you wanted to, but personally, I find the Macaulay duration easier to work with. I think it's easier to calculate. And if you don't remember, this is the formula for the Macaulay duration. It looks pretty complicated at first, but it's actually not too bad. It's just the sum of the present value of the cash flows multiplied by the time at which they are made. All right, that's the numerator at least, and then it's divided by the present value of the cash flows. So the Macaulay duration of the assets will be equal to our cash flow of $1,000 times X at time equals 1. So we'll have time 1 times 1,000 times x times the present value factor to the first power, and that will be added to the second cash flow, which is made at time equals 3. So we'll have 3 times 1,000y, and remember we want the present value of that cash flow, so we will have v cubed. And then this is divided by the present value of those two assets, or of those two cash flows, which is exactly what we have right here. All right, so we'll have 1,000 times x times v plus 1,000 times y times v cubed. Okay, so that's the Macaulay duration of the assets, but now we need the Macaulay duration for the liabilities. And in this case, we only have one liability to work with here, so this is actually going to be pretty simple to set up. The Macaulay duration of the liabilities will be equal to the present value of that liability multiplied by the time at which it is made, or the time at which it is paid. So we'll have 2 times 2 multiplied by 53,000 v squared, and that will be divided by the present value of that liability, which is just 53,000 v squared. Okay, now what the second condition for immunization tells us, and this is for both Redington and full immunization, is that the Macaulay duration of the assets needs to be equal to the Macaulay duration of the liabilities. And so we can set these two expressions equal to each other, but notice that we already set the present values equal to each other, which is what we would be doing in the denominator here of these two expressions. So we don't need to do that again. That would be a little bit redundant and unnecessary. And so really all we have to do to create a second equation to work with here is to set the numerators equal to each other. Right? We're already saying that in order to be immunized, the present values of the assets and liability need to be equal. So assuming that is true, then in order for the durations to be equal, these numerators should be equal. So here's the actual second equation that we will work with. We will set this numerator equal to this numerator and have 1,000 x times v plus 3,000 y v cubed, and that will be equal to 2 times 53,000 times v squared, which will give us 106,000 v squared. Okay, so now what we have are two equations that we can use to solve for x and y, which are the amount of the 0 coupon bonds that the company needs to buy in order to achieve immunization, or more specifically in this case, full immunization, since their liability is sandwiched between two assets. Okay, so we use the different conditions of immunization to set up these two equations. All right, now there's a couple different ways that we could go about solving for x and y here, but the way that I'm going to choose to go about it here is to subtract the top equation from the bottom equation. So if we do that, what we'll have is 1,000x times v minus 1,000x times v. That will be 0, and that will be added to 3,000y times v cubed minus 1,000y times v cubed. Those are like terms, so we'll have 2,000yv cubed, because 3,000 minus 1,000 is 2,000, and that will be equal to 106,000 v squared minus 53,000 v squared, which is just going to give us 53,000 v squared. All right, so all we did there was subtract this equation from this equation. It's a technique that you learn in algebra for solving a system of equations. Okay, now the reason we did that is because by subtracting this equation from this equation, we eliminated x from the resulting equation. Now all we have to do is solve for y, and then we'll have one of our variables that we can then plug into another equation to solve for x. All right, so let's solve for y in this equation. I'm going to work with it over here. All we have to do to solve for y is divide both sides by 2,000 v cubed. So if we do that, we'll have that y is equal to 53,000 v squared divided by 2,000 v cubed. All right, now notice that we have v squared in the numerator and v cubed in the denominator. We can make evaluating this a little bit easier for ourselves by factoring out a v squared from the numerator and denominator. And then we can also reduce the numerator and denominator by a factor of 1,000. And so after doing that, y will become 53 divided by 2v. And if you remember, the present value factor, v to the power of t, is equal to 1 divided by 1 plus I to the power of t. And so if we have v to the first power, then this is equal to 1 divided by 1 plus I to the first power. which will just be 1 divided by 1 plus I, and I is 0.05 in this case, so we'd have 1 divided by 1.05. All right, so this V would be 1 divided by 1.05, but remember that dividing by a fraction is the same as multiplying by its reciprocal, so instead of dividing by 1 divided by 1.05, we can just multiply 53 halves by 1.05. So here's what we'll have. We'll have 53 divided by 2 times 1.05. That is what y is equal to, and if you plug that into your calculator, you will find that y is equal to 27.825. All right, so that's y. Now that we know that y is equal to 27.825, we can use that value and plug it into one of these two equations to solve for x. Now I'm going to choose to plug y into this first equation here. So here's what we'll have. We'll have 1000x times v plus 1000 times y, which is 27.825 times v cubed, and that will be equal to 53,000 v squared. Now, in order to solve for x, the first thing that we need to do is subtract this term from both sides of the equation. So we'll have 1000x times v is equal to 53,000 v squared minus 1000 times 27.825 times v cubed, and that will become 27,825 times v cubed. And then to solve for x, we just need to divide both sides by 1000v. And so if we do that, I'm just going to erase this and write x, and then I'm going to erase this, and we'll say that x is equal to these two terms divided by 1000v. All right, now I'm not going to go through the same process of reducing all of these terms. Just remember that v to the power of t is equal to 1 divided by 1.05 to the power of t. And so remembering that, you can plug this expression into your calculator, and if you do that, you will find that x is equal to 25.238 and some more decimals. So that is what x is equal to. Okay, so at this point, we have actually completed this problem. We have now found the answer that we were looking for. We wanted to determine how many 1-year zero coupon bonds and 3-year zero coupon bonds the company needed to purchase so that the liability is immunized at 0.05, or an interest rate of 5%. And we have now found that the company needs to purchase 25.238 1-year zero coupon bonds, that's X, and they need to purchase 27.825 3-year zero coupon bonds, that is what Y is. Okay, and if you wanted to check to make sure that these are the correct answers, what you could do is plug them back into one of these two equations to see if they hold true. Right, if we plug in this value for y in this equation and this value of x into this equation, this side should be equal to this side. Or another way that you can think about it, if you watched my lesson video on this topic, is that the net present value function should be equal to 0, and the net present value function is just equal to the present value of the assets minus the present value of the liability. So that would just be these two terms minus this term. And if that's equal to 0, then you know that x and y are the right answers. Okay, and I should be more specific here. We're looking to see that the net present value function evaluated at 0.05 is equal to 0, and you should find that that is true. Okay, and if you wanted to mess around to see if the company truly achieved immunization, meaning that their net present value function is not going to be less than 0 given a change in the interest rate, what you could do is plug in different values for I into that net present value function, and you should find that the net present value will never be below 0. So that's something that you could do for fun. You could plug in 0.06 or 0.07 or even 0.01, or you could try 0.1, whatever you want really. For whatever interest rate you plug in, since we achieved full immunization here, you should still have a positive result for the net present value function. Okay, and once again, that's just equal to the present value of the assets minus the present value of the liabilities. Okay, and so with that, that is it for this example. And so let's take a look at one more example for this video. Okay, so here's our second example. A company has liabilities of $500 in 1 year and $1,000 in 4 years. The company sets up an investment program to match the duration and present value of their liabilities using an effective annual interest rate of 10%. This investment program produces asset cash flows of X today and Y in 3 years. Find X and Y and determine if the investment program satisfies the conditions for Redington immunization. All right, so this problem is a little bit different than the previous example. Last time we were told that the company wanted to immunize their liability. In this case, we're not exactly sure if that's what they're doing. We will have to determine that at the end to see if their investment program satisfies the conditions for Redington immunization. However, we are told something pretty interesting. We are told that the company sets up an investment program to match the duration and present value of their liabilities using an effective annual interest rate of 10%. That's interesting because what that tells us is that the duration and the present value of the assets and liabilities are going to be equal with the way that the company set up their investment program. And so it almost sounds like they are trying to immunize their liabilities. But remember that for Redington immunization, there is one more additional condition related to convexity. So we are going to have to check that, but we'll wait till the end. The first thing that we want to do is determine the amount of the asset cash flows of X today and Y in 3 years. So the first thing that we should do here is set up a timeline and draw in where those assets lie and where the liabilities are located as well. All right, so let's draw our timeline. There's time equals 0, and I'll draw it to be about that long. Now, in this case, we only need to account for 4 years in the timeline because the company has a liability of 500 in 1 year and 1,000 in 4 years, but their assets are X today and Y in 3 years. So we're only looking out to 4 years in the future at most. So we'll have time equals 1, time equals 2, time equals 3, and time equals 4, and I'll label them. Here's T equals 0, T equals 1, T equals 2, T equals 3, and T equals 4. Now, once again, I'm going to put the value of the assets at time t above the timeline and the value of the liabilities at time t below the timeline. And I'll start with the liabilities. We have 500 in 1 year, so that's 500 at t equals 1. So we'll write in 500. And then we have 1,000 in 4 years, so that will be 1,000 at t equals 4. So we'll have 1,000 right there. Now, the company sets up their investment program such that it produces asset cash flows of X today and Y in 3 years. So I'm actually going to have to move this notation right here. Just remember that the assets at time t are above the timeline and the liabilities are below, because I need to put that asset of X right here at time equals 0. All right, now just to be consistent, I'm going to put the liability at time t over here. So the assets are above, the liabilities are below. But then we have another asset of Y in 3 years. So that will be Y at time equals 3. All right, so there is Y at time equals 3. Okay, now just to make sure you understand why X is at t equals 0, whenever you were told that a payment is made today, that is referring to the present time at time equals 0. Okay, so that's why X is there and not at time equals 1. And then one more thing I want to make a note of here is that the company is matching the duration and present value of the assets and liabilities with an effective annual interest rate of 10%. So I'm going to write down that I is equal to 0.1. That is 10% in decimal form. Okay, so now we've taken a note of the liabilities and the assets. So let's set up our equations to show that the durations and present values are going to be equal between the assets and liabilities. That's what it means for the company to match the duration and present value of their liabilities. Using this interest rate of 10%, the present value of these two assets should be equal to the present value of these two liabilities, and the duration of the assets should be equal to the duration of the liabilities. And just like with the previous example, I'm going to choose to use a Macaulay duration rather than a modified duration because I find it easier to calculate, at least when we're working with a timeline like we have right here. Okay, so let's start by matching the present values. I'm going to label that with 1. The present value of the assets will just be X plus Y times V cubed. Right, the asset of X is already at time equals 0. It's already valued where the present value is valued, so we don't need to multiply it by any present value factors. And then the asset of Y is 3 years in the future, so we need to bring it back 3 years to the present, which is done by multiplying it by a present value factor to the power of 3. All right, so that's the present value of the assets, and they are going to be equal to the present value of the liabilities. And so we have a liability of 500 in 1 year. So the present value will be 500 times v to the first power, and that will be added to the second liability in 4 years, and the present value of that will be 1,000 times v to the power of 4. The present value factor to the power of 4 will bring that liability back 4 years to the present. Okay, so now we've matched the present value. Now let's do the same for the Macaulay duration of the assets and liabilities. And so I'll start with the assets. The Macaulay duration of the assets will be equal to the present value of the assets, but multiplied by the time at which they are made, divided by the present value of the assets. So what we're going to have for x is time equals 0 multiplied by x, right? It's made at time 0, so we're going to have 0 times x, and that's it for that asset, and that will be added to the time at which y is made, which is 3, so we'll have 3 times y, and then we need the present value of that, so we'll have v cubed. And then that will be divided by the present value of those assets, which, as we said earlier, is x plus y times v cubed. Okay, now for the Macaulay duration of the liabilities, that will be equal to the present value of the liabilities, but each of them are going to be multiplied by the time at which they are located. So we're going to have 1 times 500 times v plus 4 times 1,000 times v to the power of 4. The $500 liability is located at time equals 1, so you multiply it by 1, and the $1,000 liability is located at time equals 4, so it's multiplied by 4. And then they are both divided by the present value of the liabilities, which, like we said earlier, is 500v plus 1,000v to the power of 4. Okay, now what we want to do is match these two durations, these two Macaulay durations for the assets and liabilities. But when we set them equal to each other, we'll be setting both the numerator and denominator equal to each other. But remember that these denominators are just the present value of the assets and liabilities, and we've already set those equal to each other in this first equation, so we can ignore that. If these two things are going to be equal, then in order for the Macaulay durations to also be equal, these numerators are what really need to be equal to each other. We're already assuming in this equation that their denominators are the same. All right, so what we're going to do for the second equation is just set this numerator equal to this numerator. And so if I do that here real quick, this is what our second equation will look like. These are just the numerators of the Macaulay durations for the assets and liabilities set equal to each other. Okay, now at this point, we are now ready to solve for x and y. Remember, we want to find what x and y are. We want to know the value of these two assets. And notice that in this second equation, we have 0 times x. That's just going to become 0, right? So we can just erase that. That's going to be removed from that equation. And so really, we just have y in this second equation, so that's going to be pretty easy to solve for. And so if we want to do that, we need to divide both sides by 3 times v cubed, which will give us that y is equal to 500v plus 4,000v to the power of 4, because 4 times 1,000 is 4,000, and that will be divided by 3 times v cubed. All right, now remembering that the present value factor to the power of t is equal to 1 divided by 1 plus I to the power of t, where in this case I is 0.1, if you remember that, then you can plug this expression into your calculator, and you will find that y is equal to $1,413.79. And of course, I'm rounding off there, but this is approximately the value of the asset y that is received at time equals 3. All right, so now that we know what y is equal to, we can now solve for x. So let's work on that next. In order to solve for x in this equation, we need to subtract y times v cubed from both sides of the equation. And so if we do that, you will find that x is equal to 500v plus 1,000v to the power of 4 minus y times v cubed. Now remembering what the present value factors are equal to, as well as knowing that this is what y is equal to, you can plug this whole expression into your calculator and solve for x. And so if you do that, you will find that x is equal to 75.36 and some more decimals, but I'm going to round it off there and say that x is equal to $75.36. Okay, so now we have completed the first part of this problem. We have found x and y, the value of the two assets produced by this company's investment program. But But we do have one more thing that we need to do, which is to determine if the investment program satisfies the conditions for Redington immunization. Now, if you remember from earlier, and I'll put these up on the screen, the conditions for Redington immunization at a specific interest rate I equals I naught are these three conditions right here. The present value of the assets must equal the present value of the liabilities. That was our first equation, so we're good there. We don't have to check that again. We know that that's true. The second condition is that the duration of the assets equals the duration of the liabilities. We chose to use the Macaulay duration over the modified duration. And so this second condition was met from our second equation, right? We set the Macaulay durations equal to each other for the assets and liabilities, which just leaves us with this last condition that the convexity of the assets is greater than the convexity of the liabilities. And we can use the Macaulay convexity or the modified convexity. All right, so in order for the company's investment program to be Redington immunized, we need to check to see if the convexity of the assets is greater than the convexity of the liabilities. That's the only other thing that we need to check in our problem. So let's do that. I'm going to choose to use the Macaulay convexity, just like we used the Macaulay duration. I find that the Macaulay convexity is easier to calculate than the modified convexity, at least for situations where we have a timeline like this. The Macaulay convexity is actually a very similar calculation to the Macaulay duration. The only difference is that in the numerator, when we multiply the time for the cash flows, we square that time. All right, so here's what that looks like. The Macaulay convexity for the assets will be equal to the present value of our assets, but each of them is multiplied by the time at which they were made, but that time is squared. So we will have 0 squared times x plus 3 squared times y times v cubed. All right, and then that is divided by the present value of those two assets, which will be x plus y times v cubed. All right, so that's the Macaulay convexity for the assets, and we'll calculate that in just a second. Now let's look at the Macaulay convexity for the liabilities. That will be equal to the present value of these two liabilities, but multiplied by the time at which they're located squared. So we'll have 1 squared times 500 times v plus 4 squared times 1000 v to the power of 4. All right, and then that will be divided by the present value of the liabilities, which is 500v plus 1000 v to the power of 4. Okay, so now, remembering what the present value factor is equal to, you want to use that interest rate of 0.1, we can calculate each of these Macaulay convexities in our calculator. Okay, and obviously for the Macaulay convexity of the assets, you do need to replace x and y with what we found that they were equal to. But as a little bit of help, remember that 0 squared is 0 times x will be 0. So this term you don't even need to include. You just have to have 3 squared times y times v cubed divided by x plus y times v cubed. Okay, so remember to use what x and y are equal to, but then you don't need to use them for the Macaulay convexity of the liabilities because we already knew what all the liabilities are. So, if you plug these two expressions into your calculator, you'll find that the Macaulay convexity of the assets is equal to 8.40 and some more decimals, and the Macaulay convexity of the liabilities is equal to 10.006 and some more decimals. And so, remember, in order for this investment program to satisfy the conditions for Redington immunization, the convexity for the assets must be bigger than the convexity of the liabilities. But in this case, that's not true. The convexity for the liabilities is bigger than the convexity for the assets, right? 10.006 is bigger than 8.40. So that's a little bit of a problem, which means that unfortunately, this company's investment program does not satisfy the conditions for Redington immunization. All right, so you could write that out if you wanted to. I'm just going to say that it's not satisfied. All right, that's going to be my answer for that part of this problem. And obviously that means that full immunization is not satisfied either, because full immunization is a stronger immunization strategy compared to Redington immunization. The third condition is a little bit different for full immunization. It requires that every liability is sandwiched between two assets, which, as you can see in our timeline, is not satisfied. This liability is sandwiched between two assets, but this one only has bread on one side. There is no bread or other asset following this liability, so obviously full immunization is not possible as well. Okay, so that's it for this example. We found X and Y and determined if the conditions for Redington immunization were satisfied, which is everything that we needed to do for this example. Okay, and so with that, this is the last example for this video, but if you do want to see another example involving immunization, I do have one more available on my membership site, and so if that's something that you are interested in seeing, I would encourage you to look into my membership site. You'll also get access to dark mode versions of most of my videos, which means that instead of this white background that you see in this video here, it'll be a black background and generally white writing, and the colors will look a little bit different, but it is basically a dark mode version of all of my videos where the colors have been inverted. All right, so I'd encourage you to check that out. But with that, that's it for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.